Okay, hello. Hope am I audible? I am Subrata Samanta. I am a teaching assistant for the thermal physics course taken by Professor Demal Banerjee in the semesters at NPTEL. I am a PhD first year student at IIT Kanpur in the Department of Physics. I suggest you to do the calculations along with me so that you can check the answers and better understanding to the problems, so clearing your doubts, etc. So today we will they spend a lot of time to understand the phase transitions and the thermodynamics properties of the phase transitions. Okay, and do some problem related to this. Uh, okay, so far we discuss the properties of the perfect gas. I mean the real gases. Okay, without any interactions, as well as some real gases and their properties. Right? So discuss the thermodynamic properties of such gases. Okay, and we consider so today we'll consider the phase transitions and in which that uh, uh, in which that there are two phase are coexist this kind and they are thermodynamic properties. Okay, so before we start, so let me bring out my screen. So hope my screen is visible now. Okay, so my screen is visible now. So before we going to the phase transitions, I like to discuss the other thermodynamic systems, other thermodynamic properties of a various systems, right? So so till now we'll discuss the thermodynamic properties of gaseous systems or some fluid systems, right? So today we will discuss more about other systems, okay, and their thermodynamic properties. So the first law of thermodynamics for, let's say, ideal gas. Okay, so for gaseous systems we write the first law of thermodynamics for gaseous system. Gaseous system. For gaseous systems, so for gaseous systems the first law of thermodynamics, first law of thermodynamics, as the du, the change in internal energy, is TdS minus PdV, right? And we learned this formula in the few classes, last few classes. So in this chapter, so in general for any kind of systems, for any kind of systems, we write the work W. So this is it's just a dq plus dw. This is the change in heat and this is the work done, right? dw. So for any kind of systems, for other systems, dw in general, let's say x and d small x. So capital X, d small x. So this capital X is that the generalized force. Generalized force, and this small x is called the generalized displacement. Generalized displacement. So this x is the intensive variable, and this x, small x, is the extensive variable. So this is the extensive variable, and this capital X is the intensive variable. Right? So let's for fluid-like system or gaseous-like systems. So for fluid-like system, this capital X and this small x. So let's make a table. This capital X, small x, and different things. So for fluid-like systems, this capital X, the generalized force, is called that minus P. This is minus P, and this is P. So what about EW? It's minus P. For elastic rod, this is F, the generalized force, and this is the length L. So this is F dl. So in this case, there is a no minus x. For fluid-like system or gaseous-like systems, if we increase the volume, pressure will be decreases, or if we decrease the volume, pressure will increases. That's why the minus appears. But for elastic gas, if we apply the force, the length will be increases. So F dl is positive. Similarly, for the dielectric case or the electric case and magnetic case system, electric and magnetic systems, dielectric systems. So dielectric systems, this is the external field, that is the generalized force, and the displacement is the dipole moment, electric dipole moment, and it's dw is E dot and similarly for the magnetic like systems, this is the magnetic field B, and this is your magnetic dipole moment M, and this is B dot dm. So for other systems, okay, so the dw is the properties. Okay. So now going quickly into the elastic rod case. So elastic rod. So this is the elastic rod. Now going to the elastic rod systems. So consider a rod that consider a rod with cross-sectional area A, cross-sectional area A, and length is L. Okay, so the area is A and the length is L. Okay, and this rod is made from some elastic material. That's it, the elastic rod. Okay. So then, if we define the expansivity, right? So linear expansivity. Similarly, for the fluid-like system, we define the isothermal compressibility. Right. So define the linear extensivity at constant tensions. So we define linear extensivity at constant tension. Constant tension. So for elastic rod, the tension is the generalized force if constant tension is F, right? So this F is tension, and so this linear extensivity alpha F at constant tensions. So is that nothing but 1 by L delta L over delta T at constant F. So there is a fractional change of the length with temperature. That is called the linear extensivity. So this quantity is positive in most of the elastic systems, but in case of rubber, this linear extensivity is negative. Right? Okay. So that means that this is greater than 0 for metal wire. Metal wire elastic except rubber. But the rubber, for rubber, exceptions that for rubber, if alpha F is less than. So now, if we now do some thermodynamics on these systems. So, so to start the the first law of thermodynamics, start with the first law of thermodynamics, that du, the first law of thermodynamics, first law of thermodynamics, that tells that the du is T ds plus F dl for elastic rods. Right? So we consider the first the elastic rod case 1. So now, if you know that okay, so now you define the other thermodynamic potential. So this is the U is the internal energy. The Helmholtz free energy F define the other thermodynamic potential, that Helmholtz free energy F is that U minus ds. Right? So then we can write this df that minus s dt plus f dl. From that we can write the entropy F as that minus delta F over delta T at constant L, and F the tension. So F is the tension. Written expression F is the tension. So this is tension, and this F, this tension written as this delta F over delta T, delta L at constant temperature. Here is the partial differential. So now we also know that the how to derive the Maxwell equation. Right? So the with the partial derivatives of S with respect to L, that means that del to F is by del T del L equals to del to F del L del T. Right? So this implies that delta S over delta L, because F is the thermodynamic potential, this is a state function, so this is exact differentials. So it means that if is an exact differential, so this del S del L at constant temperature is minus del F del T at constant L. So this is the Maxwell equation for elastic rod systems. Maxwell like relations. So Maxwell like relations for elastic rod systems. So what is the importance of this Maxwell equations? So as in the case of gaseous systems, so Maxwell equations allows us to relate some differentials of entropy, right, to a differential which we can measure in experiments. So in the elastic rod systems, as you see that the delta S over delta L, that means the change in entropy is related to the change in tensile over the temperature. Right? So we measure the change in entropy over the length at constant temperature, that is related the change in tensile over the temperature at constant length, right? So the experimentally is hard to measure the entropy change, right? So experimentally hard to measure the change in entropy. So if we written explicitly that the experimentally hard to measure change in entropy, even if this is the very fundamental information about the system. Even if very fundamental information, even if it gives the very fundamental information about the system, fundamental entropy, so it gives the very fundamental informations about the system. So Maxwell relations helps us to measure this quantity experimentally. So Maxwell relations helps us to, so that is the power of the Maxwell equations. So Maxwell equations helps us to measure this entropy change, entropy change via the change in tensors, that is experimentally measurable through change in tensor. So which is possible to measure experimentally. It's possible. It is possible to measure. Experiment, which is possible to measure experiment. So that is the case. Okay, so that is the power of the Maxwell equations. Why we use Maxwell and why the Maxwell equations is so important. So something that is not measurable experimentally, are very hard to measure, right? And but the Maxwell equations tells that this quantity relate to some measurable quantity, and we can measure the other quantities, and from this we can measure this. So this is the case now. Yeah. So now one more thing that if as we see in the previous class, or before that, that the internal energy for the ideal gas is not changed when it expands isothermally. Okay. So at constant temperatures, the internal energy is not changes. So the question is that the internal energy, internal energy U for ideal gas, right? Because for ideal gas the U is only depends on the temperatures. So the internal energy U for ideal gas does not change when it is expand isothermally. When it is expand isothermally. Check anyone is okay. So for ideal gas does not change when it is expand isothermally. How does U changes for an elastic rod when it is expand isothermally? What about the elastic rod systems? So so the internal energy U for ideal gas does not change when it is expand isothermally. But how does U changes? U changes a change for an elastic rod system. An elastic rod when it is expand isothermally. When it is expand isothermally. Hello, if you have any question. Okay. So if at any point if you have any questions, so please ask me. Unmute yourselves and ask me. So how to write this the change in internal energy for elastic rod systems? So go into the things that du is. Yeah, we write du as TDS plus FDL. du TDS plus FDL. Then del u del L. So from this we can write this del u del L at some constant temperature T, T del S del L at constant temperature plus F. So now use the Maxwell equations that del S del L at constant temperature is minus del F del T at constant L. So this is the T minus del F del T at constant L plus F, right? So as you see that this is not zero, non-zero quantity. Okay. So the what is going on here? So this is non-zero, right? Or if we write this in terms of uh, this is a non-zero. So now if we use the partial derivative identity, that del f del t at constant L, right, minus del f del L at constant t, and del L del t at constant f, right? So this del L at constant t and del L del t at constant f, this is alpha f, right? The expansivity, linear expansivity alpha f. So we write this as a minus a times n del f delta L at constant t times alpha f, right? So this is f. Now we define the linear. Now we define the isothermal Young modulus ET. So if we define the isothermal Young modulus for the elastic rods, define isothermal Young's modulus ET. So isothermal Young modulus ET. So this is a stress by strain. So stress is that dF by A and strain is dL by L, right? So that means that L by A dF dL at constant temperatures, isothermal, right? ET. So then if we write this this del F del T L, it's nothing but I think that minus A ET alpha F. So if we put that, we get that del U del L T is E ET A T E T alpha F plus F. So A is a area, right? Plus F tensors. So if you know that the linear expansivity experimentally and F, this is a tension, isothermal Young modulus is also measured experimentally, and this area and temperatures, we calculate this del U del L at constant temperatures. Okay. Right. So what is means? What this equation implies, and how does differ from the ideal gas? For ideal gas, this will be checked, right? So this is the sum. So del U del L T is the sum of a positive term expressing the energy going into the rod by work, right? So this F and a term expressing the heat flow into the rod due to an isothermal change of length, right? So one is that the heat flow, another is the work, right? For an ideal gas, a similar expressions comes, but for the ideal gas, the work done and the heat, they are perfectly balanced, right? That's why that U does not change with it does not change. But in this case, this due to this unbalance of this heat and work, okay, the isothermal changing in the length of the elastic rods. So this quantity is non-zero. gaseous systems, you see, you know that there is a minus signs. So minus PdV, they actually perfectly balance, but in the elastic rod gas, this minus sign is not there, and so in this case both are positives. That's why this does not vanishes when the isothermal change of the lengths of the elastic rods. So similarly, so now we go into some magnetic systems. Yeah, and then we will uh, discuss the phase transitions or thermodynamics of the phase transitions. Okay. So, let's start with the paramagnetic system. So magnetic systems, paramagnetic. So consider a systems of magnetic moments, and that is arranged in some lattice, okay, at some temperature T. Consider some magnetic moments. Consider magnetic moments. Arranged in a lattice at some temperature T. Arranged in a lattice at some temperature T. Right. So assume that the magnetic moments cannot interact themselves. So if you consider the lattice, that thing is that the lattice. So every lattice point there is a magnetic moments, is a dipole moment, dipoles. And, the dipole has some magnetic moments, and these dipoles cannot interact themselves. So it is a 2D lattice, but you consider as well as a 3D lattice. So every lattice point, okay, there is a dipole, magnetic dipole. Okay, and we assume that the magnetic moments cannot interact themselves. That the magnetic moment cannot interact themselves. So now if we apply the magnetic field, so this is important at the temperatures. So the whole systems fixed at temperature T. So now if we apply the magnetic field, so magnetic moments try to line up, and this is the system is exhibited paramagnetic, right? So now the applied the magnetic field, right? Apply the magnetic field, then the magnetic moment try to line up, and the system exhibits a paramagnetism. System exhibits system is said to be exhibit paramagnetism. So then if we write the first law of thermodynamics for these systems, first law of thermodynamics, that is the first principle, first law, second law of thermodynamics. Everybody start with from the first principle. So if we write the first law of thermodynamics, for these systems, that's the du TdS plus dT, right? So in the beginning we write the generalized force and the displacement generalized and how to write the dW for particular systems. Okay. So this is a magnetic moment, and so M is the magnetic moment, and B is the magnetic field. Okay. So now if we write the Helmholtz free energy, so if we write the other thermodynamic potentials, that's a Helmholtz free energy. So if we write the other thermodynamic potential, energy F is U minus Ts. Now in this case, in the case of magnetic systems, so due to this applied field, so the magnetic energy is also appears. Right? So the magnetic energy is U is minus mb. So that means the total internal energy is U minus mb. And the Helmholtz free energy is that U minus mb minus Ts. So this minus mb is the magnetic energy. In this applied magnetic field P. So if you put a dipole moment dipole of magnetic moment M in a magnetic field B, so this dipole, the induced energy is that minus M. So then if we write that dF change, the differential change in the Helmholtz free energy is minus S dt minus M dB. So throughout this we assume that the volume is constant. Okay. So, there, so from this, we write, if we write the Maxwell equations for this case, okay. So then the del S del B. So similarly, the Maxwell equation. Maxwell equation in this case that the S and M write in terms of del F, del B, and del F del D. So this we end up with this that del S del B at constant temperature equals to delta E over delta B at constant, sorry, delta M over delta T at B and T at constant magnetic field. Right? So That means the isothermal change in the entropy with the field. Okay, so now what is the delta M delta T B? So if we define the magnetic susceptibility kappa, so the magnetic susceptibility is defined in this way that if we define the magnetic susceptibility kappa, h tends to 0. So in this case, the H is that the field, P is the magnetic, but H is also called the magnetic field strength. So that B and H differ is that B generally mu naught H plus M. So this mu naught is the magnetic permittivity. Okay. So then I can write this kappa as mu naught M by B. So this M is the magnetization. So this M is the magnetization. So H is the magnetic field strength. And M is the magnetization. So this M times V equals to the magnetic dipole moment, small m. That is the relation. Then if you write this del M del D in terms of this magnetic susceptibility, so you get that this P times P by mu naught delta kappa over delta T at constant. So that means that the entropy change again. So the entropy change is very hard to measure experimentally, but this magnetic susceptibility is measured experimentally. So that the right hand side you measure experimentally, and that related to your entropy change in the left hand side. So that is the again we see that the power of the Maxwell equations. So the heat absorbed in an isothermal change in P. So the magnetic field changes isothermally. So how to write the delta Q? The heat absorbed in an isothermal change. Isothermal change in magnetic field P. This is the delta Q, that T del S del V at constant temperatures times delta V. It's like a TDS. Okay, and we just write a because the I write this thing in terms of the delta P, change in magnetic fields. So then if we use this above relations, that del S del B T is T B B over mu naught delta chi over delta T at constant B times delta. So heat absorbed in an isothermal change in B, is it? So now what is the delta chi delta T? So for a paramagnetic systems, okay, Curies. So now, if I so the paramagnetic system, the magnetic susceptibility. So paramagnetic system. Paramagnetic system obeys Curies law. Curies law. So Curies law is kappa. It is inversely proportional to the temperatures. So that means delta kappa or delta T is negatives. So which implies that delta kappa or delta T at constant magnetic field is negative. This is negative. So that means the delta Q. So the heat absorbed, right? So heat absorbed in isothermal system, not initial. The delta Q is negative. This is the important. And if we change the magnetic field isothermally, the heat absorbed. But it's the negative sign. So if we so our sign convention is that if we see that the delta Q is negatives, right? So that means the heat is emitted. So isothermal change in B is that delta Q, and since it is negative, so it implies that it is actually emitted. Now, yeah. So if delta V is positive, right? So isothermal increases. Isothermal increase in B, the heat is actually emitted. Right? So it turns out to be negatives. So it turns out to be negative. It turns out to be negative, which implies that the heat is emitted in an isothermal increase in P. Heat is emitted in a isothermal increasing way, right? So it is emitted in an isothermal increasing. So that is called. So that is called the isothermal magnetization. Isothermal that is called the isothermal magnetization. So similarly, if we write the change in temperatures in an adiabatic change in B. Similarly, if we write similarly, if we write the change in temperatures in an adiabatic change in B, adiabatic change in B, for an adiabatic change in B, for an adiabatic change in magnetic field B, the temperature changes delta T over delta B adiabatically. So use the thermodynamic, the partial differential equation, the del T, del B, del S at constant magnetic field B times delta S, delta B at constant temperature T. So what is that del T del S at constant B? So we define the heat capacity. We define the heat capacity Cv is T del S del T at constant B, right? That means becomes that minus T B over mu naught Cv, right? And delta chi over delta T at constant. So we know that del S del T B is 1 over Cv is 1 over T del T del S B, right? So 1 over Cv is 1 over T del T del S. And if we know that the del S del Bt derived times ever, the del S del Vb is this. Yeah, del S del Vbt is Vb by mu naught del chi del Tb. Vb by mu naught. So this quantity, this del chi del T is negative, but due to this negatives, then the whole quantity is positives. So the whole quantity is positives. So that means, so this implies that we can cool a material using adiabatic demagnetization. So if we adiabatically change and the temperature is, so you can cool material using adiabatic demagnetization. So magnetic field is decreased. If we decrease the magnetic field, so the temperature is decreases. So we can cool a material using adiabatic demagnetization by reducing the magnetic field on a sample while keeping a constant entropy. So it implies cool in materials material using an adiabatic demagnetization. Adiabatic demagnetization. So these two things is very important. So cool the materials, adiabatic demagnetization. So cooling means that the reducing the temperatures, and adiabatic demagnetization is reducing the magnetic fields. Okay, good. Okay. So at the end, if I get some time, then we can discuss that briefly about rigorous discussions on the adiabatic demagnetizations and the paramagnetism, these properties. So now I'm going to discuss the phase transitions. So now we are going to discuss the phase transitions. Okay. So what is the phase transitions? So phase transition and the one thermodynamic phase changes into another thermodynamic phase. So the phases in the thermodynamically stable one phase and you go into the another thermodynamically stable phase. That is called the phase transition. So one thermodynamic phase to another. That is the one thermodynamic phase. So the phases must be thermodynamically stable. One thermodynamic phase change this into another phase. So that is phase transition. So an example is that let's say transitions from the liquid water to vapor. So vapor is like a gas phase. So if we start with a cold water, you warm it and presently get the water and then go into the gaseous state, right? So the transitions between the different phases is a very sudden. It is only when the boiling point is reached the liquid water and becomes thermodynamically unstable and the gaseous water or the steam is thermodynamically stable. So when we increase the temperatures, the one phase becomes thermodynamically unstable and the another phase becomes thermodynamically stable, and that's why the phase transitions occurs. So these phase transitions it's very sudden. Transition between different phases very sudden. Okay, very sudden. So when it reaches some at particular temperatures, the one thermodynamic phase becomes unstable and another phase becomes stable. That's why the thermodynamic, that's why the phase transitions occurs. Some temperature, it's a T. The one phase let's call that T. One phase becomes thermodynamically unstable at particular temperatures. At some particular temperatures. Some particular temperature T. One thermodynamic phase becomes one phase becomes thermodynamically unstable. Unstable. And another phase and another phase becomes stable and another phase becomes thermodynamically stable. So thermodynamically unstable and another phase becomes thermodynamically stable. That's why the phase transitions occurs. That's why the phase transitions. Okay. So suppose you increase the temperatures of a substance. Okay. At some temperatures, it changes from one phase to another. So we need some, if this change is discontinuous or there is some finite change, so we need some heat, some extra heat to do this. This is called the latent heat. So at this particular temperature is called the critical temperatures. This temperature is called the critical temperatures. Temperature is called critical temperature. Is in which both the phases are this is not a T3. So at particular temperatures, yes, but there exists some temperatures. It's called the critical temperatures. at particular temperatures, that one phase becomes thermodynamically unstable and another phase becomes thermodynamically stable, and that's why the phase tensions occurs. Now we define a temperatures. So now we define a temperatures called the critical temperatures. So now we define a temperature called temperature called critical temperatures Tc, in which both the phases are thermodynamically stable. So in which both the phases are thermodynamically stable. Phases are thermodynamically stable. Are thermodynamically stable. So that means at this Tc, at these temperatures, if we change from one phase to another, so we need some extra heat. So at Tc, if we change from one phase to another discontinuously, change one phase to another discontinuously, this is a sudden change, discontinuously. So we need to supply some extra heat. We need to supply some extra heat, it's called the latent heat. It's called latent heat. So this only appears when the phase changes discontinuously at critical temperature Tc. Okay. So which quantity changes discontinuously? We'll see in few minutes. So it's the latent heat. It's the entropy or instant entropy changes discontinuously. So it's the latent heat. It's defined that L is called the latent heat. L is the Tc at particular temperatures and H2 minus S1. This is just delta Q, the T delta S. Is a reversible. So delta Q reversible is T delta S. Just use this and I get this. At particular temperature Tc, that is the latent heat. So this is the independent of the it's not temperature dependence. Just at particular temperature Tc is Tc times that, only appears at particular some temperatures, not dependent on temperature dependency, external dependence on temperatures. So there is no external dependency on the temperature. So it's a constant temperature. Tc is a constant temperature. The L is not a function of temperatures. This is a assumption. So that the Tc is a constant temperature. constant temperatures. That is the importance. Okay. So now you define the heat capacity. So what is the heat capacity? The heat capacity is Cs. See some Cx. So yeah. So this is that the T there is del T at some constant x, right? So this x can be anything: the pressure, volume, or magnetic field. So x. X can be anything: the pressure, volume, magnetic field. It's generalized force. It's not force, but any variables. So this Cx is a function of temperatures. Right? Because S is a function of temperatures. So this Cx is a function of temperatures. And if there is a S, if the finite change in S at Tc, so this is a function of the heat capacity, a function of temperatures. This implies the finite and the discontinuity in S implies that the spike in heat capacity. So right in the next page, that the discontinuity of S finite discontinuous finite discontinuity in S implies that there is a spike in the heat capacity. Spike in the heat capacity. There is a spike in the heat capacity. Usually refer as a CP. Usually refer as a CP heat capacity at constant pressure, because this is easy to constants in the laboratory. Okay. Now we derive the Clausius-Clapeyron equations in some other way. Okay. So now we have to discuss the Clausius-Clapeyron equation, that is the applications of the first law, second law of thermodynamics. So if you have any questions, you can ask in the discussions forum. or you can ask. So all these live sessions are recorded and uploaded in the YouTube channels. So if you have any questions, so please raise these questions in the comment sections, or you can ask the discussions for post discussions for. So now we are going to discuss the applications of first law and second law of thermodynamics. First and second law of thermodynamics. So one is the Clausius-Clapeyron equations. In the first analysis. So Clausius Clapeyron equation. So until now, okay. Sorry for this internet issue. So until now, we have only considered the ideal gases, and we like to show the properties of these ideal gases, right? And we will discuss these things through this first law and second law of thermodynamics. So now we are going to discuss the thermodynamics in the medium that is not the ideal gas. This is the coexist in the two phases. So the medium that is where the coexist two phases, and we like to discuss the thermodynamics in these regions. The working medium is not the ideal gas. So the elegant way to do this. So let's consider the working medium is the working medium the coexistence of the two phases. Now the working medium is not an ideal gas. The working working medium Now the working medium is the interface of two phases. Interface of two phases. This is our working mediums, the interface of two phases. And I will like to discuss the thermodynamics in this medium. So the elegant way to do this, let's consider an elegant way to do this. Let's consider a Carnot cycles. So whatever we learned so far, we're using this using those things will derive this closest Clapeyron process. So let's consider a Carnot cycle. Let's consider a Carnot cycle operated with a liquid gas interface. Operated with liquid gas interface. Consider Carnot cycle operated in a liquid gas interface. So the vapor pressure is P and temperature T and volume V. The vapor pressure, so vapor pressure let's say P originated the PV vapor and temperature T and volume V. So cycle is operated according to the following PV diagrams. So if we draw a PV diagrams, so this 1 to 2 goes isothermally, right? So evaporating n moles of liquids. So considering this is the interface of this. Let's say this is a liquid. So this is a liquid, this is a vapor, and this interface is PV T bar. The volume is V. Now in this mediums we operate this in this interface we operate. So this is a vapor and this is a liquids, and here is the interface. So denoted as the red thing, that is the interface. Now 1 to 2 which changes isothermally, that the evaporating n moles of liquid. So 1 to 2, and so 3, so 1 to 2, evaporating n moles of liquid isothermally. Evaporating n moles of liquid isothermally, right? Two to three, say reversible cooling. Reversible cooling, right? 3 to 4, so isothermal contractions, right? So 3 to 4 is isothermal contraction. So that means that the recondensing n moles of liquid. So first evaporating, and this is the isothermal contractions. So that means that the recondensing n moles of liquid and finally 4 to 1 is the reversible heating from 4 to 1. Okay, reversible heating. So this is the fourth process in this Carnot cycle in the PV plane. So if I denote this at one point, the pressure is PV, the vapor pressure, and this 4 point, the pressure is PV minus delta P. So pressure decreases delta P amount at this 4 point, and the volume at this point 1 is V1 and point 2 is V2. Is V2. So if we observe that V2 minus V1, volume V2 minus V1 is Vg minus Vl. The volume of n moles of gas, this is a volume, this is observe that volume of n moles of gas and n moles of liquid. Volumes of n moles of liquid. Now they calculate the efficiency of these cycles. So calculate the efficiency of this cycle. Efficiency of this cycle. So how to calculate? So now it's the 1 to 2 process is the isothermal process. That means the temperature is constant. Okay, and the total volume is V2 minus V1, 1 to 2. So for 1 to 2, change in volume, V2 minus V1, it's Vg minus V1, which is constant. So that means that it does not change in volume, does not change volume, right? Does not change volume. V2 minus V1, this is just a constant. So what is the work? So the ending Dutch work. In the internet. Okay, good. So the ending, so engine Dutch work. Engine Dutch work. Delta W. So delta P, the change in pressure, delta P, times the change in volume, V2 minus V1, which is V2 minus V1, interprocess. So this is nothing but del P into Vg minus VL. So this engine does work on the outside wall in the cyclic process. So the engine does work on the outside, on the surroundings. The surrounding in this cyclic process. In this the cyclic process. So this amount of work. So the heat absorbs. So what is the heat absorbs in this process, cyclic process? So the heat absorbed is that nothing but the NL, the latent heat. So N mole of gas, the heat absorbed. So heat absorbs. It absorbs each in L. So where LP is the latent heat vaporizations of a mole of a liquid. Latent heat vaporizations of a mole of a mole of liquid. So if there is a N mole, so N times LP. So this is the heat absorbed, N times LP, and this is the work done. So now from the definitions of efficiency, so the efficiency is the efficiency eta is delta W by the heat. So delta W by Q is the heat absorbs. That is the definition. This is delta P times V2 minus V1 by N times LV. So now the important point is that so any two reversible engines, all the reversible engines has the same efficiency as the Carnot engines. That is the one of the statements of the second the implications of the second law of thermodynamics. So from the second law of thermodynamics, we derive the Carnot theorems. Okay. So the Carnot theorem tells that any reversible Carnot engines, okay, any reversible cyclic engines has the same efficiency. The efficiency is equal to the Carnot engines. Right. So let's say consider a Carnot engine that is operates between the temperature T and T minus delta T, and this efficiency, and let's consider the another Carnot engines. Let's consider another Carnot engine operating between, so let's say eta 1, let's consider another Carnot engine operating between T, the temperature, and T minus delta T. Right? So let's consider another Carnot engine which is operating between these two temperatures. Okay. So what is the efficiency in this case? So the efficiency for the eta 2 is nothing but the delta T by T, 1 minus T minus delta T by T, and after algebraic simplification is delta T by T. So that the 1 minus TL minus TS, which is T minus delta T by T. So this is the independent of the working substance. So this is very crucial. So if we saw that for the ideal gas, right, the Carnot efficiency is 1 minus TL by TH, right? The lower temperature and the higher temperature, 1 minus TL by TH. But it can do for any gas. Okay. If you consider some real gas or other working substance, the Carnot engine, if operating between the two temperatures, if the TL is the lower temperature and TI is the higher temperature, the efficiency is 1 minus TL by TH. So this is the independent of the working substance. This is the independent of the working substance. This is a very crucial point. So in this case, the working substance is a medium, that is the interface of the two phases. It's not the ideal gas medium. It's not the ideal gas. Not the ideal gas. But still we apply this. Okay. So this is valid in general. Okay. So if you consider some real gas instead of ideal gas, you end up with the same formulas. Same formula for the efficiency. So look into the literatures, and I also wrote a papers in this on this efficiency. Okay, and they consider some real gases, the Savas gas and the nitric gas, and show that this form of this efficiency is better for this complex working substance. So then we can write this. This is a delta T by T, right? So now apply the Carnot theorems. Applying the Carnot theorems. So that is the one of the equivalence of the second law of thermodynamics. So that's why we call that the applications of the thermodynamics. So apply Carnot theorems. Carnot's that all reversible heat engines have the same efficiency. So that means that eta 1 is eta 2. So eta 1 is eta 2. So which implies that del T by T is equals to del P into G minus Vn divided by LLP. So it implies that dP over dt equals to LLP, latent heat NL, divided by T times Hg minus P. For 1 mole of gas, just put that. So this is a Clausius-Clapeyron equations for N. So for 1 mole of gas, let's put M equals to 1. This is the Clausius-Clapeyron equations. Okay. So this is the Clausius-Clapeyron equations. Good. So it's a more elegant way to derive this thing. Just what we learned so far, the canonic Gibbs, second law of thermodynamics, first law of thermodynamics. That's the implications of this. So this tells that the slope of the vapor pressure curve. So it's very interesting that which gives the slope of the vapor pressure curve, right? So you could then measure the vapor pressure curve for various substances and compare the measure of the slope with the Clausius-Clapeyron equations. Right. So what is this equation? So this measure which gives the slope of the vapor pressure curve. So this PV is a vapor pressure, changes this kind of thing. The slope of the vapor pressure curve. It changes the vapor pressure PV to PV minus delta P. Right. So let's say for the PV vapor pressure. So which gives the slope of the vapor pressure curve. So we could then measure this vapor pressure curve for various substances, working substances. So consider various working substances and measure these vapor pressure curves. Okay. And compare the measuring slope from the Clausius-Clapeyron equations. So the measure the vapor pressure curve experimentally. So experimentally measure the vapor pressure curve. Pressure curve for various substance. And compare with the measured slope to that, and compare it with the measured slope to the Clausius-Clapeyron equations. Clapeyron equations. Clapeyron equations. So this is the one of the way to experimental prove the general validity of the first of the problem. One of the way. So this is the experimental proof of the general validity. Experimental proof of first and second law of okay. So on what things we have to discuss that what is the Gibbs phase rule. So Gibbs phase rule that we want to find out how much freedom of a system has to change in its certain parameter while keeping the different substance in various combinations of phases in equilibrium with each other. Right. So how much freedom? So what? How to calculate the degree of freedoms? So we want to input this possibility having a mixture of different substance. Okay. And we call them the different substance as a components. So Gibbs phase rules, the way to find out tells that how much degree of freedom of a system. So, okay, so the component is that the mixture of different substance and the different substance is called component. So, so let's see the mixture of different substance. Mixture of different substance. It's called the components. So this different substance, which is called components. So component is a chemically independent constituents of a system. So components is a chemically independent independent constituents of the system. Constituents of the systems. So the Gibbs phase rule states that if there is a C components, the multi-component system, let's say consider a multi-component system. Consider a multi-component system containing C components. So consider a multi-component systems containing C components. That means that the multiple chemical constituents, the C components, and P is the phases, different phases, and P different phases. Different phases. Then the Gibbs phase rules say then the number of degree of freedom, the Gibbs space rule tells that the number of degree of freedoms of the system, then number of degree of freedom if of the system if it's C minus P plus 2. We'll derive in the next class that in more elegant way. This is the Gibbs space rule. So this is the Gibbs. This is the Gibbs space rule. So let's say for a single component systems, let's do on examples for a single component systems. That means that C equals to 1. This implies that F is 3 minus P. Right? So if there is a one phase, that if there is a one phase, that means P equals to 1. So which implies that F equals to 2. Okay. So that whole PT plane is accessible. Yeah. So for the phase transitions, P and T are the variables, right? Because the Gibbs P energy is dependent on the P and T. Okay? And this Gibbs P energy does not change. That's why the P and T becomes. So PT plane is accessible. The whole PT plane is accessible. So whole PT plane is accessible. The number of degree of freedom is 2. Is a plane. Second, suppose let's say the two phase coexist, then this implies that F equals to 1. So that means the line, the coexistence line in the PT plane. Coexistence line in the PT plane. Coexist line in the PT plane. Okay. That is only the accessible. So now if the P equals to 3, the 3 phases, so it implies that F equals to 0. So only one point at the 3 phases coexist. This is called triple points. So one point, so only one point where 3 phases coexist. So this is called the triple point. So this is called this point is called the triple point. So in this way, the Gibbs space rule identify that how much degree of freedoms. How much freedoms? How much freedom of the systems has to change the internal parameters. So I hope you can solve the assignment problems with these things. It's not very hard to calculate these things. So you just use the formula and put. So using the process periodic equations and this Gibbs space rules, just put into the okay, we can calculate things that you want. Okay. So okay, so let me stop here. Thank you. We will see in the next series. Bye bye.